In this video, we will learn what nanoparticles are, how to identify them, and describe some of their properties and uses. The word nanoparticle is a combination of nano and particle. Nano, in everyday language, indicates that something is very small, even smaller than the micro version. In science, nano is used as a special prefix for units, and it means a billionth of. You might see this expressed as 1 divided by a billion, 1 divided by 10 to the power of 9, or 10 to the power of minus 9. 1 nanometer is equivalent to 10 to the minus 9 meters, and 1 billion nanometers is equivalent to a meter. You might see nanometer abbreviated NM. So does that mean that a nanoparticle is a billionth of a particle? How does that work? Particles don't have a restricted size. What about nanometer-sized particle? That makes sense. However, that wouldn't be very useful. There aren't going to be very many particles that are exactly 1 nanometer in size. Instead, scientists use the word nanoparticle to describe anything that's roughly evenly shaped and between 1 and 100 nanometers in height, width, and depth. So, in order to be a nanoparticle, it must be able to fit inside a box that's 100 nanometers by 100 nanometers by 100 nanometers. Almost any solid substance can be made into a nanoparticle. You could make nanoparticles of salt, nanoparticles of gold, even nanoparticles of wood. Some nanoparticles are actually single molecules. There's a form of carbon called Buckminster fullerene, which is a perfect shell of 60 carbon atoms that's about 1 nanometer across. But exactly how small is a nanometer? Well, let's start with something you can imagine, a 1 meter long ruler. Cut it in half, and what you'll be left with will be 50 centimeters long. Halve it again, and it's 25 centimeters long. If you keep on cutting and halving, you'll eventually get to something that's 1 nanometer long, and that will take 30 cuts in total. So how does this compare to the size of other objects? At one end, we have a piece of coal that's about 5 centimeters across that can fit in the palm of your hand. At the other end, we have a single atom of carbon that's about 1/4 of a nanometer across. We can take the big piece of coal and grind it into smaller pieces. Particles between 2,500 and 10,000 nanometers are called coarse particles. If we keep grinding, we'll eventually get to the level of fine particles, which are between 100 and 2,500 nanometers. And if we're very persistent, we might break those particles into nanoparticles, between 1 and 100 nanometers in size. The next thing we're going to look at is how many atoms or ions you might find in a nanoparticle. There are many types of nanoparticle, and some of them have very unusual structures. As particles get smaller, the atoms or ions don't fit together quite as well as they do when the particles are bigger. To keep things simple, let's look just at metal nanoparticles. Particles of metal tend to keep the same structure as they get smaller. To keep things interesting, let's look at a few metals at once: lithium, potassium, and cesium, 3 of the alkali metals. And let's have a look at how many atoms we'd expect to find in a particle that has a diameter of 1 nanometer, 10 nanometers, or 100 nanometers. In a 1 nanometer lithium particle, we'd expect about 24 atoms, but a 1 nanometer particle of cesium would only have 5. A 1 nanometer particle has a strict volume. We can fit fewer big atoms and more small atoms in the same volume. We can fit many more atoms into a larger particle, so in a 10 nanometer lithium particle we expect about 24,000 atoms, and in a 10 nanometer cesium particle we expect only 4,600. And we get another big jump when we increase the diameter by a factor of 10 to 100 nanometers, with 24 million lithium atoms or 4,600,000 cesium atoms. But bear in mind, these are estimates based on how we see metal atoms fit together at larger scales. But what we can see is that nanoparticles can have very few atoms, like 5 atoms in a 1 nanometer cesium atom, or very many atoms, like 24 million lithium atoms in a 100 nanometer particle. Now we know what nanoparticles are and how to describe them, but why did we bother giving them a name in the first place? Often, when chemists give something a name, it's because of how it behaves, but nanoparticles are not a group of similar substances. Nanoparticles tend to behave differently to larger particles of the same substance. We expect substances like alkanes to exhibit similar chemical behavior. So let's imagine we take a substance and we turn it into a nanoparticle. And we compare it to another substance that we've also turned into a nanoparticle. The chemical properties of that little nanoparticle are going to be more like the larger particle of the same substance than a different type of nanoparticle. Now, let's have a look at the things that make nanoparticles special. The first feature is that they have much higher surface area to volume ratios than larger particles, making them much more reactive. Let's imagine we've got a sugar cube that is 1 centimetre along each side. The volume of the cube is 1 centimetre multiplied by 1 centimetre multiplied by 1 centimetre, 1 centimetre cubed. A cube has 6 faces, and each face is 1 centimetre by 1 centimetre, so the total surface area is 6 centimetres squared. This gives us a surface area to volume ratio of 6 square centimetres for each cubic centimetre. Now let's imagine we've got exactly the same volume, so the same amount of material, but broken into cubes that are 100 nanometre by 100 nanometres by 100 nanometres. Like I said, we're using exactly the same amount of material, so it has the same volume. But each particle has much more exposed surface, and the total surface area is 600,000 centimetres squared. This gives us a surface area that's 100,000 times bigger. So neglecting any other factors, simply because they're so small, nanoparticles are likely to be more reactive, more flammable, and better catalysts. You can use less material to have the same surface area and the same catalytic activity. Visible light has a wavelength between 700 and 400 nanometers. When we shrink substances down to the nanoparticle size, some of them absorb light more and some of them absorb light less. On the human scale, gold is shiny and of course golden, but gold nanoparticles interact with light in special ways and look red when suspended in solution. But meanwhile, titanium dioxide is a white pigment used in paints, but nanoparticles of titanium dioxide suspended in water or spread thinly in sunscreen are invisible to the human eye, but they still absorb hazardous ultraviolet radiation. The final important feature of nanoparticles is that they are small enough to go where bigger particles can't. Nanoparticles can get into human cells, where they can deliver medicines, be tracked by UV light, or be triggered to destroy cancer cells. They can also be used to lay down microscopic circuitry. However, we can't easily predict how nanoparticles might behave in the human body or the environment, so we have to be careful to test them first. Even if we know that larger particles are safe, that doesn't mean that nanoparticles will be too. As a society, we need to be mindful about which nanoparticles we release, because some of them can do a lot of damage and build up in the ecosystem enough to kill plants and animals. We now know about nanoparticles, what makes them special, and how to describe them. Let's have some practice. A human hair has a diameter of 80,000 nanometers. How many nanoparticles with a diameter of 50 nanometers would fit across the human hair? Give your answer to the nearest whole number. Human hair varies in thickness by quite a lot, but it's typically 100 micrometers wide, which is about 100,000 nanometers. The particular hair we've been given is 80,000 nanometers in diameter, which is just a little bit thinner. Nanoparticles are particles with a diameter of 1 to 100 nanometers. The nanoparticles we'll be using have a diameter of 50 nanometers. I've assumed in this case we're dealing with spherical nanoparticles. Our job is to work out how many of these nanoparticles placed end to end would fit across the human hair. This means we need to work out how many particles in a line are 80,000 nanometers long, and we shouldn't overthink it and place the nanoparticles on the surface of the hair. To figure out the number of nanoparticles we need, we simply have to take the diameter of the hair and divide it by the diameter of the nanoparticle. We plug in our values to get 80,000 nanometers divided by 50 nanometers. We don't necessarily need a calculator for this because we can see that 50 goes into 800 16 times, which means 50 goes into 80,000 1600 times, giving us our answer of 1600 nanoparticles. And we already have our answer to the nearest whole number. Our next question looks at the applications of nanoparticles in sun creams. Nanoparticles are used in sun cream. Which of the following reasons is not an advantage of adding nanoparticles to sun creams? A. Nanoparticles in sun creams provide better protection against UV rays. B. Nanoparticles in sun creams give better skin coverage. C. Nanoparticles in sun creams result in a transparent liquid. D. Nanoparticles in sun creams are absorbed deeper into the skin and provide longer protection. Or E. Nanoparticles in sun creams may be washed away into the environment. Nanoparticles are particles that are 1 to 100 nanometers in size. Sun creams generally contain particles of titanium dioxide, which are there to absorb UV light and help prevent sunburn. Our job is to identify which of the 5 statements is not an advantage of adding nanoparticles of titanium dioxide instead of large particles to sun creams. The first statement suggests that nanoparticles in sun creams provide better protection against UV rays than larger particles. It's hard to see how the size of particle is going to affect how well it absorbs ultraviolet light, so I'm going to come back to this statement later. The second suggestion is that nanoparticles in sun creams give better skin coverage. On first look, it looks like big particles will cover a surface just as well as small particles. But skin is actually quite rough and uneven. Smaller particles will fit into the holes and gaps much better than bigger particles. And you'll use a smaller mass of particles to cover the same surface area. And it's a clear advantage that nanoparticles give better skin coverage in sun creams than larger particles, so this is not our answer. The next suggestion is that nanoparticles in sun creams result in a transparent liquid. Large pieces and large particles of titanium dioxide are white, but nanoparticles are smaller than the wavelengths of visible light, and titanium dioxide nanoparticles appear colourless in a thin film or in solution. So nanoparticles in sun creams don't turn the liquid white, which from a commercial perspective is a bonus, because people don't want white streaks on their skin when they apply sun cream. The next suggestion is that nanoparticles in sun creams are absorbed deeper into the skin and provide longer protection. Nanoparticles of titanium dioxide can get into the gaps in your skin much deeper than larger particles, and therefore stick around longer and provide longer protection. Therefore, this too is true. And we can see how being absorbed deeper, providing longer protection and giving better skin coverage would make nanoparticles in sun creams provide better protection against UV rays than larger particles. This leaves us with the final suggestion that nanoparticles in sun creams may be washed away into the environment. On first glance, this does look like an advantage. You don't want to have sun cream caked to your skin after you come home from the beach. However, while large particles of titanium dioxide are considered safe, it's not been proven that nanoparticles are safe in all situations. It may be that we find it damages the environment in ways we haven't yet understood. So, until we know better, we should be wary about putting nanoparticles into the environment. Now, let's round off with the key points. A nanoparticle is simply a very small particle of matter with a diameter of 1 to 100 nanometers. 1 billion nanometers is equivalent to a meter. Nanoparticles can be made from many different substances. Some nanoparticles are safe, some are hazardous, and for many we have yet to find out. Nanoparticles have much higher surface area to volume ratios than larger particles. This generally makes them react more quickly than larger particles and be better catalysts. Some nanoparticles interact with light in special ways, meaning we can get unique behaviour from a material that seems very ordinary. And finally, some nanoparticles can go into places that larger particles simply cannot.